All right. So on to 10.3. We're going to talk about hypothesis tests for a population mean. We have talked about just kind of hypothesis tests in general in 10.1. And then in 10.2, we talked about hypothesis tests for a population proportion. So here we're going to talk about hypothesis tests for a population mean. And it's a very similar process to 10.2, testing for a proportion. So the first thing we're going to do is state our hypotheses. The next thing we're going to do is calculate a test statistic. And again, this test statistic is basically a z-score that corresponds to your sample statistic that you collected. In this case, x bar, since we're trying to test a hypothesis regarding means. Once you have your test statistic, then you can use it to compute a p-value. And again, you have a different p-value that you're going to compute depending on whether you're running a two-tailed, left-tailed, or right-tailed test. And then finally, you'll use your p-value to make a decision. And just like in the previous section, if the p-value is less than alpha, then you reject the null hypothesis. Okay. Last but not least, of course, we write a conclusion based on the decision that we make. Let me see if I can make this less blurry. I don't know if that's any better, but okay. So then we write a conclusion. Just like with testing proportions, we would have conditions that we would need to check here in order to run the test. In 10.2, I didn't make a big deal of checking those conditions, and I'm still not going to in this section so much, but there will be, I think, a problem or two that we're going to have to be careful about. And so we'll talk about checking conditions a little bit more in this section than we did in the previous one. This first example here is an example of actually doing these computations up here by hand. And I'm not sure I want to do that. I think I'm just going to let, just like in 10.2, I'm going to let StatCrunch do this for us. So here's the StatCrunch procedure. Okay. Again, very similar to the way that we compute confidence intervals for the mean. Right? We're going to go to stat, and then t-stats, then one sample, and then either with data or with summary. So let's do that here on example 1. It says the mean height of American males is 69.5 inches. The heights of the 44 male US presidents, Washington through Trump, have a mean of 70.1 inches and a standard deviation of 2.77 inches. Excuse me. Okay. Treating the 44 US presidents as a simple random sample of all US presidents, past, present, and future, determine if there's evidence to suggest that US presidents are taller than the average American male. Okay, so step 1, we're going to state the hypotheses. Oh, as far as checking conditions are concerned, we need our sample size to be at least 30. Our sample size in this case is 44. Right? It says treating the 44 US presidents as a simple random sample. So so that condition is met. Okay, so we can go ahead and run the test. All right, so our null hypothesis. Now we're not testing proportions anymore, we're testing means. Right, so our null hypothesis is that mu, the average height, right, is the same as it is for just American males in general, right, 69.5. The alternative is the statement that we're trying to prove, right? So we want to know if, in fact, that average is more, right, taller. We want to know if US presidents are taller than the average American male. So we want to know if mu is actually greater than 69.5. Well, What evidence do we have to potentially support this claim? Sorry. So what evidence do we have to potentially support this claim? Well, we know that the average height for US presidents is 70.1 inches, right? So our sample mean is 70.1, and that's certainly larger than 69.5. Question is it different enough? So to answer that question, we run the test. We're going to do steps 2 and 3, the test statistic and the p-value. We're going to do them in StatCrunch, right? So we go to stat, calculators, and, or sorry, not calculators. I apologize. Nope. We're going to go to stat and then t-stats. T-stats. Last time in 10.2, we were going to stat proportion stats. Now we're going to stat t-stats, right? Because we're testing means in this section. We're going to go stat t-stats, one sample with summary. Let's see what we're prompted for when we do that. So stat t-stats, one sample with summary. Ooh, we're prompted for the sample mean. We're prompted for this sample standard deviation. It says these people have a mean of 70.1 and a standard deviation of 2.77. So the standard deviation is 2.77. And then we're prompted for the sample size, which we said earlier was 44, right? Okay. So 70.1, 2.77, and 44. And now we want to test mu equals 69.5 against mu greater than 69.5. Okay, so here's our test statistic. It's about 1.44. So we'll say T naught is about 1.44. And then our p-value is 0.079. Now we use that p-value to make our decision. We make our decision by comparing the p-value to alpha. Alpha in this case was 0.05. If the p-value is less than alpha, we reject the null hypothesis. In this case, our p-value is not less than alpha, right? This is not a true statement. So we do not reject the null hypothesis. Okay. So in conclusion, we would say something like this. So at the alpha equals 0.05 level of significance, there is not sufficient evidence to support the claim that, and then here's where you insert the alternative hypothesis in words, right? So there's not enough evidence to support the claim that the US presidents are taller than the average American male. Okay, so again, your conclusion needs to contain those three pieces. You need to state your level of significance. Then you need to say whether or not there's evidence to support whatever. And then you need to restate the alternative hypothesis in words, right? So in this case, at the 0.05 level of significance, there's not sufficient evidence to support the claim that US presidents are taller than the average American male. And that's that. Okay, I think hypothesis testing is really nice. I think that it just, I think it's really cool. We're not guessing here, right? It's like if you think back to like your elementary school days and you think about the science fair, you probably collected some data and then you did some research and made some kind of hypothesis, and then you were supposed to say whether or not your data fit the hypothesis, but it was really kind of just guesswork because of course you were in elementary school, right? You didn't have all these sophisticated mathematical tools that we have now, but you don't have to guess anymore. It's like if you want to know, it's like our level of significance here is 0.05. That means that we're 95% certain that we're making the correct decision, right? We're 95% sure that there's not enough evidence to say US presidents are taller than average, right? Anyway, so I think that's pretty cool. A word about the p-value. We talked about the p-value in 10.1. We talked about it again in 10.2, and I kind of really emphasized that it's an important concept. So let's remind ourselves, the p-value here is the probability that we would get this sample statistic if in fact this were the true population mean. So if the true population mean is 69.5, then the probability that we would get a sample mean of 70.1 or greater is about 7.9%. Okay, that's low, but not low enough. If our level of significance had been 0.10, then we would reject the null hypothesis in this case. Okay. So that's that. Let's move on. Let's do another example. So this one says, according to the American Time Use Survey, the typical American spends 154.8 minutes, that's 2.5 hours, per day watching television. Do internet users spend less time each day watching television? I mean, we're all internet users now, right? Except maybe our great-grandparents are, if they're still alive, or our grandparents in my case. Well, let's see. So a survey of 50 internet users results in a mean time watching television per day of 128.1 minutes. That is quite a bit less, with a standard deviation 46.5 minutes. Determine if internet users spend less time watching television. Okay, so null hypothesis is that they don't spend less time. They spend the same amount of time as everyone else watching TV. Okay. The alternative is that they do spend less time watching television. And the sample evidence that we have to support that claim is that this particular sample of 50 internet users had a mean time of 128.1. So let's see, that is definitely less than 154.8. Is it different enough? Well, let's get the p-value. We're going to go to stat, t-stats, one sample with summary. Then we're going to tell StatCrunch that the mean is 128.1. The standard deviation is 46.5. And the sample size is 50. Let's see what we get. And yes, right, our p-value is tiny. Okay? In other words, the probability that we would get this if this were true is practically 0. That tells us that our assumption must be wrong, so we reject it. Okay? So our p-value is less than 0.0001. Since 0.0001 is less than 0.05, right, which is our level of significance, we reject the null, right? Again, it's very important to me that you understand the logic here. So I'm going to repeat it. Okay, so again, this is the probability that we would get this result if in fact this were the case. In other words, if we assume that the true mean is 154.8, then the probability that we would get a sample mean of 128.1 is practically 0. That tells us that our assumption must be wrong, so we reject it. Okay? Okay, so in conclusion then, we would say this. State our level of significance. This time we have evidence that the alternative is true, right? We're rejecting the null. That means there's evidence to support the alternative. So at the 0.05 level of significance, the evidence suggests that the alternative hypothesis is true. Well, what was the alternative hypothesis? The alternative hypothesis is that internet users spend less time watching television, right? So the evidence suggests that internet users spend less time watching television. Now, before you go patting yourself on the back because you're thinking, I'm an internet user and so I spend less time watching television. First of all, that's not necessarily true. But second of all, probably the reason that internet users spend less time watching television is because they're on social media or YouTube or whatever else, right? So it's not necessarily that they're like out in the world doing something amazing, right? They just have a different way to entertain themselves than to sit around watching TV. Okay, so that's that one. Let's look at another one. By the way, I guess I should say, if you want to try these problems out before I work them out for you, then do so, right? Pause the video, work out the problem. That would actually be a really good thing to do to see if you understand the concept, right? So I'm going to let you pause the video and see if you can work this one out on your own. So pause the video now if you want to do that. I would encourage you to. But now I'm going to go ahead and work out the solution. Right, so it says, the student suspects the average cost of a one-bedroom apartment in Visalia is no longer $675 per month. To test her hypothesis, she randomly selected 16 apartment complexes and found that they charge an average of $685 per month with a standard deviation of $23 per month. Okay, so that is larger. Is it different enough? We'll see. At the 0.10 level of significance, is there enough evidence to support her claim? Now here it says, assume the population is normally distributed. And they have to tell us that because our sample size is not big enough for us to run this test unless we're allowed to assume that the population is normally distributed. So it's good that they're giving us this information. Otherwise, we wouldn't be able to run the test. But we can run the test because they tell us the population is normally distributed. So we'll go ahead and do so, right? we're going to state our hypotheses. The null hypothesis is that the average price has not changed. Okay, it's still $6.75 just like it always has been. The alternative, well, it says the student suspects that the average cost is no longer $6.75. It doesn't say that she suspects that it's greater than that. It doesn't say that she suspects that it's less than that. It just says that she suspects that it's different than that. So we're going to run a two-tailed test here. Well, what sample evidence does she have to support this claim? Well, she went out and collected a sample and got a sample mean of 685. Right? That's different than 675 to be sure. Is it different enough? Let's see. We go to stat, t-stats, one sample with summary. We'll enter the sample mean. We'll enter the sample standard deviation. We'll enter the sample size. Let's see what we get. Okay, there's our p-value. That's not going to be small enough for us to reject the null hypothesis, but just barely. See, alpha is our cutoff point, right? We need to be smaller than this number, and we're not. We're just a little bit bigger than that number. Okay, so we're not going to be rejecting the null hypothesis. Okay, so our p-value, 0.1025. In other words, if we assume the true population mean price is 675, then the probability, then there's a 10.25% chance that we would just so happen to select 16 apartment complexes whose average price is 685, right? So if we assume 675 is the true mean price, then the probability we get a sample mean price of 685 is 10.25%. That's not a small enough probability for us to doubt the assumption that we made here, so we do not reject it, okay? Okay, so we do not reject the null hypothesis. Since we're not rejecting the null hypothesis, that means that there's not enough evidence to support the alternative, right? We're not rejecting the null, so we don't have evidence to support the alternative, okay? Okay. So at the 0.10 level of significance, there's not sufficient evidence to claim that the average price of apartments is different than 675. Cost of a one-bed apartment is no longer 675, right? There's not enough evidence to support that claim. Okay. So that's that one. I think I have one more example for us to do. And I want to go through this example because it's one where we have data instead of a summary. We actually have raw data. So this one says, according to the United States Mint, quarters weigh 5.67 grams. A researcher is interested in determining whether the state quarters have a weight that's greater than 5.67 grams. He randomly selects 8 state quarters, weighs them, and obtains the following data. In addition to that, we're given this normal probability plot and this box plot. The reason they might give you this is to help you determine whether or not the data comes from a population that's normally distributed. What you're looking for is you need the dots to all be pretty close to the line. In this case, they are. And you need for there to not be any outliers. And in this case, there are not. So the conditions are met. Okay. So, so let's run the test. The null hypothesis is going to be that the state quarters weigh the same amount as the normal quarters. That is, that they weigh 5.67 grams, right? So the null hypothesis is that mu equals 5.67. And the alternative hypothesis is that mu, well, the researcher is interested in determining if their weight is greater. He thinks the state quarters might weigh more. He thinks they might weigh more than 5.67 grams. What sample evidence does he have to support this claim? Well, it's right here. Okay, he hasn't done any work so far to summarize the results of his survey. So we'll have to enter this data so that we can get our sample information from there. So I'm going to go ahead and enter this data now. Okay, and let me just make sure that I got those in correctly. Just double checking my work. Okay, I think that looks good. And now we're going to run this test in StatCrunch. So we're going to go to Stat, T-Stats, one sample. And this time we don't have a summary, we have the raw data. So we're going to say with data. So let's do that. Stat, T-Stats, one sample with data. You have to tell StatCrunch where the data is stored. Okay, I stored it in this column here. And then we need to write our hypothesis, the hypothesis test we want to run. So we want to write tell test. Okay, and then we hit compute. So there's our sample mean, in case you're interested, right? So our population mean was 5.67. The sample mean for this particular set of state quarters was 5.70. And that is larger. It's larger by 0.03 grams. So, so there is a difference there. Is it different enough? Well, yeah, right? The probability, this is the probability that we would get this sample mean if in fact the true population mean were 5.67. Right? So there's only a 0.6% chance of that happening. That's really small. And what that tells us is that our assumption that we made in the null hypothesis must be false, right? So we reject it. So let's write some things down. What was our level of significance here? Well, it didn't say, did it? We weren't given a level of significance. It doesn't really matter though. This p-value is so small. The most common level of significance, there are three most common ones. They're 0.10, 0.05, and 0.01. The smallest of those is 0.01, and this is even smaller than that. So whatever we choose for alpha, we're going to be rejecting the null hypothesis. It doesn't really even matter. I'm just going to say we're definitely rejecting. Okay. So at the 0.01 level of significance, the evidence suggests that, well, we're rejecting the null hypothesis, so that means there's evidence to support the alternative, right? So the evidence suggests that the alternative is true, that the state quarters weigh more than the normal quarters. And that's that.